Hello everyone, welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. Hope all the videos that have been posted by me till date have been useful for you. In this video, we are going to study about electrostatic potential, potential difference, potential energy, then we'll calculate the electric potential due to electric dipole, potential energies of different charge configurations. We'll study about equipotential surface, and then lastly we'll pick up is the electrostatics of conductors. So for the first part we pick up with line integral of electric field. Now when we say line integral of electric field, then what do we mean? We have to have a figure here which shows that a source charge is placed at the origin O. Here in the electric field produced by the source charge, we have a point A and a point B. Point A described by the position vector RA and point B described by the position vector RB. Now we are supposed to calculate here what would be the value of line integration of electric field. Now we want to transport a unit positive charge from point A to B. The entire length of the path is divided into small intervals of length dl. Now direction of dl vector is along the direction of the tangent at point P. So here theta represents the angle between what we call as r vector and dl vector. Now in the figure, the distance OP dash, that is from O to P dash, it can be made as OP plus PP dash. Now the distance OP is equal to R and the distance PP dash by the resolution of dl vector is obtained as dl cos theta. Now this is a small increase in the value of R, so we can call dl cos theta as dr. So we here have written here OP distance by R, OP distance as R plus dr. Remember PP dash has been taken as dr. Dr is nothing but a small increase in R, and magnitude wise dr would be equal to dl cos theta. Now what would be the electric field due to the source charge? The electric field would be given by kq upon r square. K can also be written as 1 upon 4 pi epsilon 0, and the electric field becomes 1 upon 4 pi epsilon 0 q upon r square. Now what would be the work done in displacing the charge q0 through a very small distance dl? Then work done must be equal to force into dl. Force would be equal to q0 times E. So E is the electric field produced by the source charge and the force is being experienced by the test charge. Now what is the work done per unit positive test charge? It would be given by dw upon q0, which would be equal to E dot dl. Now I need to calculate what is the total work done in moving a unit positive charge from point A to B. The total work done would be given by integration dw upon q0, and the integration ranges from point A to B E dot dl. Now this part, that is integration A to B E dot dl, is called as line integration of electric field. We need to calculate what would be the work done in moving a unit positive charge. So E dot dl can be written as E dl cos theta. Now dl cos theta, we can replace it by R. What was the value of electric field? kq upon r square. The position vector for A point is RA and for B is RB. Now k and q are constant, we have to integrate r power minus 2 dr, which is minus 1 upon r, and the limits ranging from RA to RB. So simplifying, we get W would be equal to kq 1 upon RA minus 1 upon RB, and we term it as equation number 2. This equation number 2 provides the work done in transporting a unit positive charge from initial point, that is RA, to the final position RB. Now question is, what is the utility or importance of the line integral? The line integral, integration E dot dl from RA to RB, represents the work done in moving a unit positive charge in the direction of electric field. Now, work done by the electrostatic force would depend only on initial and final positions and is independent of the path, and that is why we say electrostatic force is a conservative force. That is, since the work done depends only on initial and final positions, so we can say the force is conservative. The same thing we did somewhere in gravitation in the earlier classes. Now we are in a position to define potential difference. How do we define potential difference? We say potential difference between 2 points A and B is equal to the work done in carrying a unit positive charge from point A to B against the electrostatic force. So, work done in moving from A to B upon Q0 is minus integration A to B E dot dl. VB final potential minus initial potential. Why the negative sign? Because we are working against the electrostatic force. From equation number 1, E dot dl was equal to KQ into 1 upon RA minus 1 upon RB. Presence of the negative sign, what it makes is 1 upon RB minus 1 upon RA, which is here. So potential difference VB minus VA could be written as KQ into 1 upon RB minus 1 upon RA. So equation 3 represents the potential difference between point A and B respectively. What is the unit of potential difference? Normally the unit of potential difference is volt. How do we define? We say the potential difference between 2 points B and A is said to be 1 volt if 1 joule of work is required to move a positive charge of 1 coulomb from point B to point A against the electrostatic force, keeping other charges in equilibrium. Here 1 volt is equal to 1 joule upon 1 coulomb. So the unit of potential difference is volt, and simply defined as, that means between B and A the potential difference is said to be 1 volt if 1 joule of work is required to move a unit positive charge from point B to A against the electrostatic force. Now the second term that comes to us is electric potential. So potential difference means difference of potential between the 2 points. And what is electrostatic potential? Potential at a given point. How do we define? To define potential at a point in an electric field, we choose a reference point at infinity. And why do we choose infinity? Because at that point the potential is supposed to be 0. This seems to be justified because a charge distribution will produce 0 field at infinity. Electric field is KQ upon R square. If I put R is equal to infinity, the electric field becomes 0. So potential at that point can also be taken to be 0 and can work as a reference potential. Now what is the definition? The potential at point B in an electric field is equal to the work done in bringing a unit positive charge from infinity to point B against electrostatic force, keeping the other charges in equilibrium. So earlier it was work done in moving a unit positive charge from point A to B. Now it is infinity to point B. Now what is the unit of potential? It has the same unit as that of potential difference. The unit of potential is once again volt. How do we define 1 volt of potential difference? So we say the potential at a point B is said to be 1 volt if 1 joule of work is required to move a positive charge of 1 coulomb from infinity to point B against electrostatic force. Once again 1 volt would be equal to 1 joule upon 1 coulomb, and the dimensions are M1 L2 T power minus 3 ampere power minus 1. Electric potential energy. The work done in moving a given charge Q0 from point A to B against electrostatic force without acceleration is equal to the difference of potential energy between the points B and A. Till now in the potential and potential difference we have been using a unit positive charge, and now here it is a given charge Q0. So by the definition of potential difference, WA to B upon Q0 would be equal to VB minus VA. So multiply by Q0 on both sides, I obtain work done in moving the charge Q0 from A to B would be equal to Q0 into VB minus VA, which is nothing but potential energy at B minus potential energy at A. So what is the SI unit for potential energy? It would be joule. And what are the dimensions? Have the same dimension as that of work, M1 L2 T power minus 2. Now for the first time we try to calculate what would be the potential due to a point charge. So how did we define potential? Work done in bringing a unit positive charge from infinity to that point. So we have to bring a unit positive charge from infinity to point P, and the entire length of the path is divided into small intervals dx, A to B. At the point A, the direction of the electric field is to the right. Since we are moving Q0 from infinity to point P, so at point A, the direction of dx would be to the left along the sense of motion. The angle between the direction of electric field and the direction of small displacement dx is 180. So we have defined it. We consider a charge Q greater than 0 be placed at point O. To calculate the potential at P, we need work done in moving a unit positive charge from infinity to point P against electrostatic field. Electric field at a point A due to charge Q. So E would be given by KQ upon X square along OA. Now what is the work done in moving a charge Q0 through a distance dx? So work done would be equal to force into displacement. Q0 E dx cos theta. Remember, theta is 180, so cos of 180 would be minus 1. Now I get dW would be now equal to minus Q0 E into dx. And what is the value of electric field? KQ upon X square. Now, if I want to calculate what is the total work done in moving a charge Q0 from infinity to point P, then I must integrate both the sides. So work done in moving the charge from infinity to P would be equal to minus KQ0 infinity to R 1 upon X square dx. Integration 1 upon X square would be minus 1 upon X, the limits ranging from infinity to R. If I substitute the limits, I have the work done as KQ0 upon R. So what is the potential at point P? It would be given by KQ upon R. Now, what inferences can we draw from this relation for potential? We find out potential is a scalar quantity and it has a SI unit volt and the dimensions are M1 L2 T power minus 3 ampere power minus 1. The potential for a positive charge, that is Q greater than 0, is positive, and for a negative charge it is negative. The variation of potential and electric field due to a point charge can be graphically represented as, for a point charge the electric field was equal to KQ upon R square and the potential is given by KQ upon R. The potential decreases at a lesser rate as compared to the electric field. So see, potential decreases at a smaller rate and electric field decreases at a faster rate. At the point of intersection, that is R is equal to 1 meter, I think E would be equal to V. That is why at the point of intersection here, we are in a position to say that electric field and potentials are equal at this point. Now we need to calculate what would be the potential due to an electric dipole. So we consider a dipole of dipole moment P. If O is the center of the dipole and the potential at arbitrary point P would be equal to sum of the potentials produced by the positive and the negative charge at point P. So we have a dipole here. This represents the negative charge minus Q, this represents the plus Q charge. We need to calculate potential at an arbitrary point, that is point P. The point P described by the position vector R, the point A described by the position vector RA, and B described by the position vector RB. Now what will the total potential at point P due to? Potential due to positive charge and potential due to negative charge. That is what we have written. Potential at point P is equal to potential due to positive charge plus potential due to negative charge. Now let us see. Keep due to positive charge it is equal to KQ upon RA, and due to negative charge it is K minus Q upon RB. Can be written as KQ into 1 upon RA minus 1 upon RB, and this is equation number 1. Here, by the geometry of the figure, we are supposed to calculate what would be the values of 1 upon RA and 1 upon RB. So we pick up the triangle OAP. Now, O to A and A to P are the two sides of the triangle taken in order. Therefore, their sum must be represented by the third side taken in opposite order. So in triangle OAP, I can write it as OA vector plus AP vector would be equal to OP vector. OA is nothing but A. This is RA and this is R. Now I need RA. So RA can be written as R minus A. So what is the magnitude of RA? It would be under root of RA square plus A square minus 2 RA cos theta. Instead of under root, I can write the power half. Now what happens for a point dipole? For a point dipole or an ideal dipole, R is very much greater than A. That is why A square is negligible. So this A square can be neglected. Now 1 upon RA would be equal to 1 upon R, 1 minus 2A cos theta upon R, power is minus half. Using binomial expansion, what can I do is, from binomial expansion says 1 upon x power n would be equal to 1 plus n times x. Using that, I get the equation 1 minus power was minus half. So that is n times the x, and x was 2A cos theta upon R. Simplifying, what we obtain is 1 upon RA is equal to 1 upon R plus A cos theta upon R. Similarly, in the triangle OBP, OB plus BP would be equal to OP. So A vector plus RB vector must be equal to R. Once again, we are interested in calculating RB. So it would be given by R vector minus A vector. And what is the magnitude of it? It would be under root R square plus A square minus 2AR, and the angle now becomes is 180 minus theta. Cos of 180 minus theta is minus cos theta. Once again, apply the conditions of ideal dipole. So this A square can be neglected. So RB would be equal to R square plus 2AR cos theta raised to power half. Take R common, it would be 1 plus 2A cos theta upon R. Now, take the inverse and use binomial expansion. So we get 1 upon RB would be equal to 1 upon R plus 2A cos theta upon R raised to power minus half. Use binomial expansion here. So 1 plus minus half 2A cos theta upon R. This 2 cancels out. So I'll get 1 minus A cos theta upon R, and we call it as equation number 3. Now we are supposed to substitute the values of 1 upon RA, 1 upon RB from equation 2 and 3 in equation number 1. So here what we get is KQ upon R into 1 plus A cos theta upon R minus 1 A cos theta upon R can be written as KQ upon R 2A cos theta upon R, and what is Q into 2A called? The dipole moment. So I must be allowed to write it as KP cos theta upon R square. What is theta? Angle between P vector, that is dipole moment vector, and the position vector R. So KP cos theta can be written as KP vector dot R vector upon R cube, or it could be written as KP vector dot R cap upon R square. So these are the different ways of expressing the potential. Now what do we find? The potential due to dipole now depends on nature of medium surrounding the dipole through epsilon. Dipole moment of the dipole, that is P. It also depends upon distance of point of observation, that is R here, and the angle theta between P vector and R vector. So these are the factors upon which the electric potential due to dipole would depend upon. Now what happens at the axial point? At the axial point means which lies along the axis. That means this point P must now be along the axis, and along this direction theta would be equal to 0. So at the axial point theta comes out to be 0, cos 0 would be equal to 1. In that case, potential at the axial point would be equal to Kp upon R square. At the equatorial point theta would be pi by 2. So cos pi by 2 would be 0. Therefore the equatorial field would come out to be 0. On axial point, it can be on the other side. So in that case, theta would be 180, cos 180 would be -1. So axial may be equal to minus kp upon r square. Now, hope that आपको ये कैलकुलेशन इलेक्ट्रिक फील्ड ड्यू टू डाइपोल समझ में आया होगा. अगर आपको हमारे वीडियो अच्छे लगते हैं तो आप इनको लाइक करिए, आप इन पे कमेंट करिए, इनको चैनल को सब्सक्राइब करिए, बेल आइकन के बटन को प्रेस कीजिए ताकि अगले वीडियो का नोटिफिकेशन आपको सही समय पर मिल जाए. प्लीज़ लाइक द वीडियोस, comment on the videos and subscribe the channel and press the bell icon button to obtain the notification at the correct time whenever the new video is uploaded. Now we would like to calculate potential due to system of charges. Here we have a charge Q1, Q2, Q3 and N. Q1 at a distance R1 with respect to point O, at a distance R2 with respect to the origin, and for the nth charge at a distance Rn from the origin. So that is what we have written. The potential due to system of charges Q1, Q2, Qn with position vectors R1, R2, R3, Rn is equal to a scalar sum of potentials produced by the individual charges at that point. So calculate individual potentials and simply sum them up. So V must be equal to potential due to first charge, second charge, third charge and the nth charge. So it is KQ1 upon R1, KQ2 upon R2, KQ3 upon R3, KQn upon Rn can be expressed with the help of a summation sign. V would be equal to summation I is equal to 1 to n KQi upon Ri. Now the question comes up is, what will be the potentials due to continuous charge distribution? If you remember, we had three types of charge distribution: the line charge distribution, the surface charge distribution and the volume charge distribution. Now the potential due to continuous charge distribution V would be given by K integration dq upon R, and integration dq to be decided by the type of continuous charge distribution. For a line charge, integration dq would be equal to integration lambda times dl, because the line charge we describe in terms of linear charge density lambda. So potential would be now given by K integration lambda dl upon R. For a surface charge distribution, integration dq would be equal to integration sigma dot dl over the entire surface area. So potential is now V is equal to K integration sigma dA upon R. For a volume charge distribution, we can say the potential would be given by K integration rho dV upon R. This integration extends over the entire volume. Now we have an idea about electric field. Like electric field for a point charge was KQ upon R square. Electric potential due to the point charge was equal to KQ upon R. Now we need to calculate a relationship between electric field and electric potential. Here, to determine that relation, what we do is we choose two closely spaced equipotential surfaces A and B with the potentials V and V plus dV. So this is the surface A with the potential VA, which is equal to V. This is the surface B with a potential VB, which is V plus dV. The distance between point A and B is equal to dr, and this gives the direction of electric field. What we want? We need to move a unit positive charge from the surface B to the surface A against the electric field along perpendicular distance dr. So work done in moving a unit positive charge from point B to A is equal to VA minus VB, that is V minus of V plus dV, that is minus dV. Similarly, work done in moving a unit positive charge from point B to A would be given by minus E dot dr, that is E dr cos theta. Theta is 180, cos 180 would be minus 1, and therefore work done would come out as E dot dr. From equation number 1 and 2, the LHS is same, so RHS can always be equated. E dr is minus of dV, so E can be written as minus dV upon dr. Now what important conclusions can we draw from the equation E is equal to minus of dV by dr? First one, electric field is in the direction of decrease of potential. Whatever is the direction of decrease of potential, the same would be the direction of electric field. The magnitude of electric field is equal to the change in magnitude of the potential per unit displacement normal to the equipotential surface at that point. So, two things that have come up is electric field is in the direction of decrease of potential, and secondly, the magnitude of electric field is equal to the change in the magnitude of potential per unit displacement normal to the direction, that is equipotential surface. Now the question that comes to my mind is, what is equipotential surface? An equipotential surface with a constant value of potential at all points on the surface. So a surface on which potential remains the same at all points on the surface would be called as equipotential surface. Now, what are the important characteristics of the equipotential surface? The first one, the work done in moving a unit positive charge from one point to another on an equipotential surface would be equal to 0. So what is work done? It is Vb minus Va. Since on the equipotential surface each point has the same potential, so potential difference comes out to be same and 0. The work done in moving a unit positive charge from one equipotential surface to another would be equal to difference of the potentials of the two surfaces. If Q0 is equal to 1 coulomb, then I'll get WA to B would be equal to simply VB minus VA. For any charge distribution, the equipotential surface through a point is normal to the direction of electric field at that point. Question is, if the field is not normal to the surface, then it will have a non-zero component along the surface. To move the unit positive charge on the surface, then work has to be done. This is in contradiction to the concept of equipotential surfaces. And that is why what we say is, for any type of charge distribution, equipotential surface through a point would always be perpendicular to the electric field at that point. The equipotential surfaces indicate the regions of strong and weak electric field. Magnitude of electric field is equal to dV by dr. That is, E is inversely proportional to dr. If dr is small, that means electric field is high. Dr means distance between the two equipotential surfaces. So crowded surfaces, they represent the strong electric field, while the widely separated surfaces, they indicate the weak electric field. Normally, the two equipotential surfaces do not intersect each other. If they intersect, then there will be two directions of electric fields perpendicular to each other, which is not possible. At the point of intersection, we will have two directions of electric field, which is not possible. Now we need to draw different shapes of the equipotential surfaces for different types of charge distributions. Like we have this as the equipotential surface for a point charge. For a point charge, equipotential surfaces are spherical surfaces centered at the charge. So these are concentric spheres as the equipotential surfaces for a point charge. This represents the equipotential surfaces for a uniform electric field. For a uniform electric field along x-axis, the equipotential surfaces are planes uniformly spaced normal to the x-axis in the yz plane. So the surfaces are perpendicular to the direction of electric field. In the first figure, it represents the equipotential surfaces for a dipole. This is the charge plus q and this would be the charge minus q separated by a certain distance, making a dipole. Similarly, this figure represents the equipotential surfaces for a system of two identical positive charge. So this also q greater than 0 and here also q greater than 0. This represents the different shapes of equipotential surfaces for an electric dipole and for the system of two positive charges. Now, we have been asked what would be the equipotential surfaces for an electric field increasing along z direction. So we can say electric field increasing along z direction, the equipotential surfaces are the xy plane. Since the field is increasing, so the distance between the planes would be decreasing. So we have equipotential surfaces which are xy planes with a decreasing distance between them. Now we need to calculate potential energy of a dipole. So we select a dipole here, A, B. At A we have minus Q charge and at B we have plus Q charge. The direction of the dipole moment is from point A to B. The electric field is in this direction. The positive charge would experience the force in the direction of field and the negative charge would experience the force opposite to the direction of field. What does the angle theta represent? It represents the angle between dipole moment vector and the electric field vector. Now we consider here a dipole of dipole moment Q, P is equal to Q into 2A, placed in a uniform electric field E. When a dipole is placed in a uniform electric field, it experiences a torque. What is the role of the torque? The work done, the torque tries to rotate the dipole. So work done by the external torque in rotating the dipole from an angle theta to theta plus d theta would be equal to dw in t is equal to integration of tau d theta. What is the value of the torque? P is sine theta d theta. Now we need to calculate what is the total work done in rotating the dipole from an initial angle theta 1 to a final angle theta 2. So we need to integrate this equation. So total work done is integration dw, integration P and E are constant, theta 1 to theta 2 sine theta d theta. Integration sine theta d theta is minus cos theta. Substitute the limit. We obtain the expression as Pe cos theta 1 minus cos theta 2. This work is stored as potential energy of the system. We can now find potential energy with an inclination theta of the dipole. If theta 1 is 90 and theta 2 is theta, then from equation 1 we will have U at the angle theta Pe cos 90 minus cos theta. Can be written as minus Pe cos theta or minus P dot E. Why do we select theta 1 is equal to pi by 2? Because it's a reference position where the potential energy of the dipole is taken to be 0. Now, case 1. If theta is 0, then what will happen? The dipole would be aligned parallel to the direction of electric field. The electric dipole moment and electric field are in the same direction. The net force on the dipole 0. The torque is supposed to be minimum, would be 0, and the potential energy is also minimum, that is minus Pe. So the position in which the potential energy comes out to be lowest and negative, then the system is said to be in stable equilibrium. So this defines the position of stable equilibrium of the dipole in the electric field. Now in the second option, theta can be equal to pi by 2. Theta can be equal to pi. In that case, the direction of electric field and the dipole moment are opposite to each other. In this case, still the net force is 0, the torque is minimum, but in this case the potential energy is maximum plus Pe. When the potential energy of the system is positive and maximum, then the system is said to be in unstable equilibrium. How do I define unstable equilibrium? A small displacement from this position, then the dipole would be aligned back by itself parallel to the direction of electric field. That is why when after a small displacement the system is not returning back to its original position, so it's said to be unstable equilibrium. In the third option, we have theta equals pi by 2. In that case, the net force is 0, torque is maximum, but the potential energy is 0. And the condition in which the potential energy becomes 0, it's neither maxima nor minima, then it is called a condition or a state of neutral equilibrium. Correct? Hope you are understanding whatever we are doing under the heading of potential, potential difference, potential energy. अगर आपको हमारे वीडियो में फिजिक्स समझ में आ रहा है तो मेरा आपसे रिक्वेस्ट है कि हमारे इस वीडियो को लाइक करिए, इसको कमेंट करिए और चैनल को सब्सक्राइब करिए। Now we want to calculate potential energy of a two-charge system. Now, potential energy of a two-charge system is numerically equal to the work done in bringing the charge Q1 and Q2 from infinity and placing them at respective position. तो इस सिस्टम को बनाने में जितना एनर्जी लगेगा that would be called as the potential energy of the system. पहले चार्ज को we have to transport from infinity to point A और सेकेंड चार्ज को वी हैव टू ट्रांसपोर्ट फ्रॉम इंफिनिटी टू पॉइंट बी. नाउ व्हाट इज द पोटेंशियल एनर्जी ऑफ द सिस्टम? इट सेज वर्क डन इन ब्रिंगिंग Q1 फ्रॉम इंफिनिटी, दैट इज वी हैव टू ब्रिंग द चार्ज Q1 फ्रॉम इंफिनिटी एंड प्लेस इट एट A अगेंस्ट द इलेक्ट्रिक फील्ड. सिमिलरली वर्क डन इन ब्रिंगिंग Q2 फ्रॉम इंफिनिटी टू B. So work done from infinity to A in bringing Q1 and Q2. But what is the work done in bringing Q1? It comes out to be 0. Why? In absence of any charge, there is no external field against which work has to be done. So the work done comes out to be 0. Without any work being done, Q1 is now placed at point A. This would produce an electric field in space against which the work needs to be done now. So the first charge will produce potential at point B in space. And that potential would be given by K Q1 upon R at point B. Now work done in bringing Q2 from infinity to point B, it would be Q2 into potential at B due to charge Q1. So that is Q2 times V. So Q2 times V is K Q1 upon R. So the potential energy of a two charge system is K Q1 Q2 upon R. So total potential energy, it comes out as K Q1 Q2 upon R. What does this potential energy depend upon? It depends upon the magnitude and polarity of the charges, distance of separation between the charges, and the nature of medium. Now if Q1 Q2 is greater than 0, then potential energy is positive. For like charges, electrostatic force is repulsive, and a positive amount of work is required to be done against this force to bring the charges from infinity to their respective position, and therefore potential energy increases as R decreases. If Q1 Q2 is less than 0, then potential energy is negative, and in that case, unlike charges, electrostatic force is attractive. Here potential energy will decrease as R increases. We have put a note here. The final expression for the potential energy is independent of the manner in which the configuration was assembled. The potential energy is the characteristic of the present state of the configuration and not the way the state is achieved. Remember, the final expression for potential energy is independent of the manner in which the configuration was assembled. इसका मतलब है potential energy इस बात पर डिपेंड नहीं करती है कि वो Q1 Q2 का जो सिस्टम हमने बनाया है वो किस तरह से बनाया गया है. So we wrote potential energy is the characteristic of the present configuration and not the way it was achieved. Now we try to transfer the result to potential energy of a three charge system. Now three charges can be assembled either in the linear chain or can be arranged in a triangular manner. Potential energy of a three charge system would be total work done in assembling the system. So the work done in bringing the charge Q1, Q2 and Q3. So Q1 into potential at A plus Q2 into potential at B plus Q3 into potential at C. Now it would be Q1 into 0. Why? Because there was no charge. So no potential existed at point O. Once we place Q1 at point A, then it would produce some potential at point B, and that would be K Q1 upon R12. Now the second charge has been placed at point B. So there are now two charges which would be producing their potentials at point C, and their potential are given by K Q1 upon R13 and K Q2 upon R23. So the total potential energy of a three charge system is given by K Q1 Q2 upon R12 plus K Q2 Q3 upon R23 and K Q1 Q3 upon R13. So this equation number A provides me potential energy of a 3-charge system. Now what are we supposed to do? We are supposed to calculate what would be the potential energy of a n-charge system. Now from the above expression, I could be allowed to write K summation over Qi Qj ranging from 1 to n. That is what I have done here. From the above relation, we can judge the relation for potential energy of an n-charge system. Summation I is equal to 1 to n, j is equal to 1 to n, k Qi Qj upon Rij. Now we'll use this equation number 1 to derive the potential energy relation for 3-charge system. For a 3-charge system, if I take I is equal to 1, then j can have two possible values 2 and 3. If I take I is equal to 2, then j can have the two values 3 and 1. If I take I is equal to 3, then j can have the values 1, 2. So what are the possible combinations of the charge? Q1, Q2, Q1, Q3, Q2, Q3, Q2, Q1, Q3, Q1 and Q3, Q2. There are 6 combinations. But in the expression, we had only 3. So 1, 2 and 2, 1, they are identical. Similarly, 2, 3 and 3, 2 are identical. 3, 1 and 1, 3, they are also identical. That means each term is coming twice. So on the basis of this, we are expecting 6 terms for the potential energy of a 3-charge system. But equation A shows that it has only 3 terms. So out of 6 terms, expected each term is coming twice. So you need to normalize the number of terms in the expression of equation 1. And that is why we are using a factor of half to reduce the number of terms from 6 to 3. So this represents the final expression for potential energy of n-charge system. What is the utility of factor half? The factor half has been introduced for the normalization of number of terms obtained in the expansion of summation of expression of potential energy. So potential energy expression में जो number of terms आते हैं उसके normalization के लिए we have utilized a factor half. Here we have a question for you. It says calculate the potential energy of a 4-charge system given here, that is a square of side A. So we have a square 1, 2, 3, 4 and the 4 charges have been arranged like this. Alternate positive and negative charge. Now for I is equal to 1, the possibilities are 2, 3, 4. For I is equal to 2, 3, 4, 1. For I is equal to 3, 4, 1, 2. And for I is equal to 4, 1, 2, 3. So combinations are 1, 2, 1, 3, 1, 4, 2, 3, 2, 4, 3, 4. And all the other terms would be the repetitive terms. So potential energy of the system is given by K Q1 Q2 upon R12, K Q1 Q3 upon R13, K Q1 Q4 upon R14, K Q2 Q3 upon R23 plus K Q2 Q4 upon R24, Q3 Q4 upon R34. Substitute the values of Q1, Q2 and the distances. So the first term it says K minus Q upon A. Then Q1 Q3 K minus Q upon root 2A. Then K minus Q upon A. K Q and minus Q upon A. K Q upon root 2A. And K minus Q upon A. So these 4 terms are identical. So we write it as 4K Q upon A. And these 2 terms are also identical. So I can write 2KQ square upon root 2A. Just take KQ square upon A common. It's minus 4 plus root 2. So potential energy could be given by root 2 minus 4, which would always come out to be negative. What does the negative sign show? Such a given system is a stable system. And in physics, such a system is basically called as quadrupole system. So what types of systems do exist in physics? A monopole exists, a dipole exists, and a quadrupole. There is something called as tripole. So we do not have a stable 3-charge system. Now let us think about electrostatics of conductors. Now we need to know what happens when a conductor is placed in a uniform electric field. Then the following results can be summarized. In case of conductor, all free electrons are found to live on the surface of conductor. Then on the surface of a charged conductor, what we find is the electrostatic field is normal to the surface at every point. If E was not normal, it would have a component, non-zero component along the surface. Then what will happen? The free electrons would experience a force and move, which is never possible in electrostatics. So how do we save ourselves? By having electric field perpendicular to the surface. Then inside the conductor, since all the charges are living on the surface, inside the electric field is zero. The electric field intensity and the volume charge density inside the conductor is zero. All charges living on the surface, so no charge present inside the surface of the conductor. The electrostatic potential is constant throughout the volume of the conductor and has the same value as inside on its surface. So the value of potential is same at every point on the surface of conductor, which is equal to potential on its surface. If the conductor is charged, then the electric field is perpendicular to the surface. The electric field at the surface of a charged conductor E is given by sigma upon epsilon 0 n cap. That means if you place a metal in an electric field, it behaves like an equipotential surface. This property we use under the concept of electrostatic shielding. Shielding means making something safe from a field. We consider a conductor with a cavity with no charges inside the cavity. Now electric field inside the cavity is supposed to be zeros because there are no charges, whatever be the size and shape of the cavity. The electric field inside the cavity is zero irrespective of whatever be the charge on the conductor and external fields in which it might be placed. Because electric field inside the cavity would be decided by the value of the charge inside the cavity. Since it is absent, electric field would be zero. And this electric field will not depend upon what is the magnitude of the charge outside on the surface of the conductor or what is the value of the electric field in which the conductor is placed. Even in a conductor, even if a conductor is charged, even if a conductor is charged or charges are induced on a neutral conductor by external field, all the charges would always live on the outer surface of the conductor with the cavity. Whatever charge you give, under whatever condition you give, but all the charges would live on the surface of the conductor. None of the charges will be made to move inside the cavity. Whatever be the charge and field configuration outside any cavity in a conductor remains shielded from outside electric influence. The field inside the cavity is always zero. This is known as electrostatic shielding. That is unaffected by any external field or any external charge on the surface of the conductor. Now, where do we use it? This is used to protect the sensitive instruments from external electrical influence by enclosing them in a metallic container. That means if you want to transport a suppose electrically sensitive machine, then enclose it in a metallic container and transport it. The entire metallic container may become an equipotential surface and therefore would save the inside machine from any external work done. Now we need to calculate what is the potential of a conducting sphere. We have a sphere of radius r. O is the center of the sphere. The distance of the point inside the conductor is pi. O pi. On the surface it is equal to the radius, and for the external point it is equal to r. Now for an external point, the charge distribution behaves like a point charge. So we can directly write the potential k, q, and the distance is OP0, which is r0 here. So for a point on the surface, the potential would be given by Vs is equal to kq upon OPS and equal to radius. At an internal point, the electric field is zero because no charges are present inside the sphere. Electric field in terms of potential can be written as minus dVi by dr. If EI is 0, then dVi must be 0. Integrate both the sides. Then what do I get? Integration dVi would be 0 or Vi would be constant. The electrostatic potential at all internal points is constant throughout the volume of conductor and is equal to the potential on the surface of conductor. Vi and Vs would be equal to kq upon r. So हर अंदर वाले पॉइंट पर इलेक्ट्रो पोटेंशियल कांस्टेंट आएगा और कितना आएगा? इक्वल टू द पोटेंशियल ऑन द सरफेस ऑफ कंडक्टर. अ वेरी इंपॉर्टेंट रिजल्ट. नाउ वी होप दैट यू हैव clearly understood the concepts of potential, potential difference and potential energy. The concept of equipotential surface and the electrostatics of conductors. If this video you have understood the physics clearly, then you are all requested to please like, comment and subscribe the channel and press the bell icon button so that you can receive the notifications in time. Thank you very much. See you in the next video. Thanks.